Okay, continue our discussion about the magnetic field and the magnetic force that results from it. I actually want to talk about energy at this point, but it's going to be kind of a short discussion, at least the first part of this, and that's because of the following very important thing to notice. So we just talked about how the magnetic force is perpendicular to the velocity, right? It's always in this third dimension. So it's perpendicular to the velocity. So because the force is perpendicular to the velocity, the acceleration is perpendicular to the velocity, and that means the acceleration is going to cause a change in direction, but not speed. So a quick little picture here. If we have an object and it's moving this way, but let's say that we figure out the direction of the magnetic force and therefore the acceleration, and it's perpendicular, right? So it's maybe going this way, right? So do you remember from first semester that acceleration, we sort of think of acceleration in two components: the component that's sort of in the direction of the line we're moving in, and then the perpendicular direction. Tangential acceleration is in the direction of the velocity, and that's the part that speeds up or slows down the object. And perpendicular acceleration is the part that turns it. That's what we call the centripetal. And so it turns out that the magnetic force can only give you centripetal acceleration. It can't speed you up or slow you down. So that's what this says. It only changes the direction, not the speed. Also, what this also implies is that it doesn't do any work. It can't do any work. So if you remember work was force times a distance, right? It was force that's applied across a distance times the cosine of the angle between the movement and the force. But this is always going to be 90 degrees, and cosine of 90 degrees is 0. This will always be 0. So there's no work being done. And of course, these two things kind of go together because there's no work being done. That also means that we can't add to that means there's no additional kinetic energy, and that's another way to think about why the magnetic force cannot speed up or slow down a particle. It can only turn it. So that means there isn't going to be any magnetic potential or potential energy, because magnetic force doesn't partake in the adding or taking of energy. It just doesn't do that. It doesn't do work. Okay? So I want to, at this point, just talk about ways in which the magnetic force differs from the electric force, things we've already mentioned. I just want to summarize this. So first of all, the electric force is always in the same direction as E, or at least in the opposite direction if you're talking about a negatively charged particle, but it's in the line of the electric field. Whereas the magnetic force is always perpendicular to the magnetic field. So that's one big difference. Another difference is that an electric field will exert its force on any particle that happens to have charge, positive or negative, even if it's not moving, whereas a magnetic field will exert its force only if the particle is moving. It has to have charge, yes, but it also has to be moving. So that's another difference. And then finally, the thing we just discussed, which is that the electric force, of course, can speed up or slow down a particle. And that is, it can do work on it, so it can increase the kinetic energy or decrease the kinetic energy. Whereas the magnetic field, the magnetic force, only changes the direction of the particle. It will not ever speed it up or slow it down, and it never adds energy or takes energy away in terms of kinetic energy. Okay. So I want to take this changing direction idea a little bit further and play it out over a period of time. We now know how force works, but force is an instantaneous thing. So let's talk about the trajectory of a charged particle that happens to be in a magnetic field. And let's assume it's a uniform magnetic field. So this time I'm going to draw a magnetic field that is going into the screen. So I'm going to draw using our convention X's, meaning going into the screen. Okay, I just made that a little bit faster. Okay, and let's say, so imagine this is just a big region of magnetic field, sort of extending to the left and right and up and down. And I'm just showing you a little patch of it. Okay, and suppose we have a particle right here going, at this moment, going this way. Okay. Now again, using our right hand rule, use your right hand and put your right hand out to the right, so your fingers are pointing in the direction of the V. But now this time you want your palm facing forward so that you can easily bend your fingers to the toward pointing in front of you, because that's the way the B field is going, right? So from V to B, and you'll notice that your thumb is pointing straight up. So there's a force going this way, which means it, although this guy's going horizontally right now, it's being accelerated upward, so it's going to start to turn. So this is the first time we're actually going to like follow this up and see where it's going to go actually. So it starts to turn. Now at this moment, its velocity has a little bit of an angle, right? So do the same thing. Now hold your fingers, instead of directly to the right, a little bit to the right, but a little bit upward. But again, with your palm facing forward, so that you can bend your fingers like toward pointing in front of you, and you'll see that your thumb now is pointing like that. So again, you're going to turn more. You're going to keep turning to the right. And what's going to happen is this is just going to continue. As you turn, the magnetic field is going to push you always to keep turning. And that's going to result in a circular trajectory. So the whole time, the magnetic force is always just turning you. It's a centripetal force. And so the result is the particle will move in a circle. It will not speed up, it will not slow down, it'll go in uniform circular motion. So that's the trajectory. That's what happens when a charged particle that is moving moves in a uniform magnetic field. Now it is important that it's uniform here, so that these forces, although they're changing direction, they're always still the same strength. That'll keep it in a perfect circle. Now we can go further with this, because we know a little bit about uniform circular motion from first semester. So if we write down Newton's second law, that force equals ma, and of course net force equals ma, but we're going to assume that the magnetic force is the only force acting on this particle, so it's just Fb. All right. So of course over here we have qvb sine theta. However, sine theta, again, notice that from V to B going straight in, that's 90 degrees. So this is a 1. So I actually don't need to write this. It's just a 1. Okay. And on the other side, I have M. And then for A, I'm going to use our circular motion, uniform circular motion fact from first semester, which is that centripetal acceleration is v squared over r. So you may remember that. I hope you remember that. Even if you don't remember the exact formula, you remember that we had a connection between a and v and r when you're moving in a circle at a constant speed. And a is v squared over r. So we're going to plug that in here. Okay, so we have qvb equals mv squared over r. One thing is we can cancel a v from each side. And so that leaves qb equals mv over r. Just to write it in a neater way without fractions, I'm going to move the r over here. So I'm going to write rqb equals mv. And so this is a very nice relationship. Again, what the assumptions going into this are that we're a charged particle moving in a uniform magnetic field. Then you have this nice relationship between how fast it's going, the strength of the magnetic field, and the radius of the circle that it will trace out. And of course the charge and mass of the object matter too. Okay, so let's try this out. We have a proton again, and it's moving in a circular orbit of radius 14.0 centimeters in a uniform 0.350 Tesla magnetic field directed perpendicular to the velocity of the proton. So we want to know how fast the proton's moving, the speed, and then, just as an added bonus, we'll figure out the period of the proton's circular motion. Okay, so again, when you're in a uniform magnetic field and you have charge and you're moving, you will go in a circle. We've established that. So let me draw a magnetic field. The exact orientation of things isn't specified here, so I'll do it like we just did it. I'll make the magnetic field go in to the screen. Okay, and then here's my proton going around in a circle. We know the radius. Okay, we want to know how fast it's going. All right, so this is actually pretty easy because we have RQB equals MV is our relationship. So if we want V, V will be RQB divided by M. R is 0.140 meters. A proton is 1.60 times 10 to the minus 19 coulombs positive. And the strength of the magnetic field is 0.350 Tesla. And we divide all this by the mass of a proton, which we just look up. Okay, and that gives us 4.69 times 10 to the 6th meters per second. So that's how fast it's moving. It's going like a little more than 4.5 million meters per second. So it's zooming around in a circle really fast. You know, a circle that we could see, 14 centimeters in radius. Now, what's the period? So period is the time it takes to go around once. So period is 2 pi r over v. So we talked about this before with circular motion, but also it's not even like its own formula. You can just think of this as its constant speed problem. So this is how far, right? This is the circumference of a circle. One time around the circle, so that's distance divided by speed gives you time. That's all this is. All right, so we have the v now and we have the r, and when you plug all that in, you get 1.87 times 10 to the minus 7 seconds, or 0.187 times 10 to the minus 6 seconds, which I'm writing just because then I can write it in microseconds, because 10 to the minus 6th is micro. So a tenth, a little less than 2/10 of a microsecond is how fast it goes around this circle. Okay,